Good morning, everyone. I welcome you all to this online seminar. The duration of this seminar will be around 1 hour. If you have any questions regarding the presentation, demonstration, or regarding the Eurocodes, then you can write down your questions in the questions window. I will be taking all your questions at the end of the presentation and demonstration. We are conducting a series of seminars focusing on the aspects of Eurocode that are critical to their implementation in Singapore. It means, along with the Eurocodes, we will also be considering the local standards like BC1, BC3 and CP83 in the discussion. This seminar is second in the series. Some of you might be new to Midas, so first of all I will give a quick introduction of the company. Midas headquarters is located in South Korea, and we have started to develop the engineering solution since 1989. Currently, Midas retains largest CA market share with more than 600 employees. As I mentioned, Midas headquarters is located in South Korea. Along with that, we have 6 corporate offices in the United States, the United Kingdom, China, Japan, India, and we opened the 6th corporate office last year in Russia. And this year, in the month of March, we opened Midas Singapore branch and we started the operations from Singapore. From now on, we will be able to look into the concerns of Singapore engineers more deeply and customize our solutions for them. And Singapore engineers will also be able to get very close and frequent technical support from us. These are 2 business areas of Midas. We are engaged in software development for bridge engineering, building engineering, geotech and mechanical engineering. And along with that, we also have engineering consultancy services for those fields. This portfolio naturally provides us a strength. Developers and engineers are having a real-time interaction. They discuss how to make the software solution more practical. Engineering consultancies using the software, and if they feel anything inconvenient or impractical in the software, they just directly go to the software developer and ask them to modify the software in a more practical and convenient manner. This helps us to focus on developing more practical solutions for engineers. These are a lineup of Midas family programs. So we have programs in building engineering, bridge engineering, geotech engineering, and mechanical engineering. Especially in the field of buildings, we have Midas Gen. Midas Gen is a 3D FEM software for structure analysis as well as design. And we have Midas D Shop. Midas D Shop is a drawing generation module. Midas D Shop can generate the drawings in the format of CP83 directly. And then we have Midas Design Plus. Design Plus is a unit member calculation program. These are Midas users worldwide. Among top 100 global engineering companies, more than 50 are using Midas as their main tool. And here you can see a partial list of the Singapore companies using Midas. And there are many other companies who have adopted Midas this year. Our support to users is one of our top priority. So we have 3 kind of support systems. The first is for self-training. Anybody can download the self-training material from our website and he can use it for studying and self-learning and growth. Then we have the technical support team. So whenever our user is having any kind of question, maybe regarding software or technical, then they write down to our technical support team and our technical support team get back to the client within 24 hours. And the third one is the online sessions. We conduct frequent and regular online training sessions. In training sessions, we discuss the topics which engineers really want to know. So just like now, every time we get some feedback from our clients, the number one compliment from them is regarding the technical support. Midas continuously conducts technical events with engineers globally. We have a very strong sense of duty that we should share the recent available technology with the engineers. And last year, we prepared a seminar in NTU. There we saw the interest of Singapore engineers towards Eurocodes. There were 870 registrations and more than 650 of them attended. Some of you might have attended this seminar. Since we have realized that Singapore engineers will have to face a new circumstance very soon, so we started the Eurocode training series 2 weeks ago. All of the Midas Eurocode training sessions will be free of charge because we truly believe that this series of session is the one you really need. Then let's begin our second session. Before going into technical details, I will introduce the model that I'll be using for the demonstration purpose today. So this is an upside down house model. And this is the model that I'll be using. Though this is a relatively simple model, but the software can handle very complex geometries as well. So here you can see that we have around 150,000 elements and we have more than 125,000 nodes. So the program can handle the complex geometries very easily. So both steel and concrete can be handled in one model file. You need not prepare different model files for that. So for today, we will be using the upside down house model. This is the flow of presentation. First of all, I will be discussing the material specifications as per BC1. After that, I'll be discussing the requirements for analysis. Do we need to take into account the sway effects or not? And do we need the second order movements or not? If we need second order movements, what method should we use to calculate the second order movements? Then we have the steel design. So we'll discuss the requirements of fluid combinations, ultimate limit state, and steel optimal design. So for steel optimal design, we will be discussing both displacement optimal design and strength optimal design. After that, we'll see report generation. So any project in Singapore using steel has to comply with BC1. BC1 provides guidelines on use of alternative structural steel to BS 5950 and Eurocode 3. So let's see what is the difference between BC1 and Eurocode 3 material properties. So here you can see that one grade of steel, let's say S235, is having more than one yield strength. The yield strength of the material S235 is changing with the thickness. As the thickness is increasing, the yield strength of the material is reducing. So in design, we need to account for this effect. So if you are using Midas Gen, then the program has the material properties as per BC1, and the program can automatically account for the reducing yield strength with the increasing strength. So you need not do manual calculations or manual specifications in order to reduce the yield strength with the increasing strength. Now this was regarding materials. Now let's see the analysis requirements. So the first thing in analysis is the structure imperfections. So let's see what kind of imperfections are there that we need to consider. First is the member imperfection. Eurocode 3 states that the member imperfections can be taken care by performing the buckling checks and adopting the correct buckling curves in the member design. In Midas Gen, we adopt the same method. We adopt the buckling curves as per Eurocode 3 in the member design. And then we have the global imperfections. Now, in order to consider global imperfection, you can apply equal and notional loads, or you can model the imperfections. So applying the equal and notional loads is a more practical method. Now further we have that we need to consider the global imperfections, or we need to consider the sway only if the horizontal loads are less than 15% of the vertical loads. So if horizontal loads are more than 15% of the vertical loads, we need not consider sway. So let's see for our model that what is the situation. Do we need to consider the sway or not? So let's perform the analysis first. And now we can compare the horizontal and the vertical. For vertical, I'll create a load combination. So containing self, dead load, live load, and for HED, yeah, we have wind load. Close. Now we can simply compare the reactions. So for HED and VED, I'll redo it. I'll specify a factor of 0.15 for every load so that we can directly compare the 15% of the vertical loads. Now I'll go to reactions. So now here we have 15% of the vertical loads and the horizontal loads. So we can see that the 15% of vertical loads is more than the horizontal loads. So this one is the case, and in this case we need to consider the sway. Let's see how we can model the equal and notional loads. In order to calculate the equal and notional loads, we need a factor phi. The factor phi is composed of three factors: phi naught, alpha h, and alpha m. So let's calculate these factors for our structure. So the phi naught is the constant value, and in order to calculate alpha h, we need the height of the structure. Let's see what is the height of the structure. So here we can directly measure the height. So we can just toggle between two nodes, and the height of the structure is 11.88. So I'll enter the height of the structure, and then we need the number of columns in a row. So let's check how many columns are there in a row. So in one row we have 5 columns. So the value of phi naught we have. Now let's see how we can calculate the notional loads from phi naught. So in order to calculate the notional loads from phi naught, we need to multiply the vertical forces with the factor phi. So in Midas, we get the results directly in the form of story axial force sum. So we can obtain the results directly. We need not do anything. So I'll create a load combination for which we want to check. So here we have the story axial force sum. So we can simply copy this and multiplying this by the factor 5. So here we have the values of the notional loads. Though these are quite small, but still we need to consider the notional loads. So now we'll apply the notional loads on our structure. So for that, I'll just choose the nodal loads. So the first value is 0.53. So we can apply notional loads on any part of the structure since we are considering the diaphragm. And then here I'll apply the second notional load, 4.4. And finally the third one, I'll apply the equivalent notional load, 2.8. So here we have applied the notional loads. Now let's see, after the notional loads, what we have to do. Now we have applied the notional loads. Now we need to check the method of analysis. So we need to see if the first order moments are sufficient or do we need to calculate the second order moments. So in order to do this, we need to calculate the sensitivity due to sway. We need to calculate the factor alpha CR. And there are two methods specified for calculating the alpha CR. The first method is FCR by FCD. We can simply perform the buckling analysis of the structure and get the alpha CR. Or else we can perform rigorous hand calculations in order to calculate alpha CR. Now if this alpha CR comes out to be less than 10, then we need to consider the second order moments. Otherwise the first order moments are sufficient. And there are two methods of calculating the second order moments. Either we can magnify the first order moments by a factor, or we can perform the P delta analysis, that is the second order analysis, to get the second order moments. Now the procedure is that first of all we'll perform the buckling analysis to get alpha CR. So here we have the available analysis type in Midas Gen. So first of all we'll perform the buckling analysis. So buckling analysis can be performed the linear buckling or the non-linear buckling, both are available. And after that, if alpha CR comes out to be less than 10, we'll perform the P delta analysis. So here are the details of buckling analysis in Midas Gen. So we can specify the load range factor and the buckling combination to be variable or constant. So we can get the results for buckling mode shape and we can get the critical load factors, both for linear as well as non-linear buckling analysis. And then we'll perform the P delta analysis is, if required, the program can perform P small delta as well as P big delta. So using the P small delta, the program can take care of the local deformations, and using P big delta, the program can take care of the global structure imperfections. And the geometric nonlinear analysis is also available. So let's perform the buckling analysis first. So here we can specify the number of modes and load cases. Now as a result of buckling analysis, we can get the critical load factors. So the critical load factor is around 9.49, so which is less than 10, and in this case we need to consider the second order moments. And as a result of buckling mode shapes, we can even get the contours for the deformation, and if we want, we can even update the model with imperfections. So here we have the critical load factor of 9.49 less than 10. So we'll perform the second order analysis, and these are the contours. These contours help us in identifying that which member is failing, so we can identify the member and change that factor if we want to increase the critical load factor. So now we'll perform the P delta. Now in design and analysis, the program will show both first and second order moments. Now we come to the Eurocode steel design. So the first thing we need in the steel design is the load combinations. So the program can auto generate the load combinations as per Eurocode and Singapore National Annex. And if we are performing the seismic design, we need to consider the orthogonal effect. Now BC3 states that if you are performing the seismic design, you need to consider the orthogonal effect either using 100:30 rule or using SRSS rule. So the program supports both of them. You can choose whichever option you want. So here in combinations, we can simply go for the auto generation of the load combinations. So I'll click auto generation, select Eurocode 3 Singapore National Annex. If want, we can consider the orthogonal effect, but in this model we are not having seismic loads. So here you can see that the load combinations are auto generated, and the steel design combinations are generated in steel design tab. And here you can see we have both strength as serviceability type combinations. So we have around 27 strength load combinations and 28 serviceability load combinations, and we can even change this to spreadsheet format for easy change of the definition. Now after the auto generation of the load combination, we need to define some specifications for the structure. The first thing is the effective length factor. So the program is capable of auto calculation of the effective length factors. So the program can check the connectivity at the ends of a member, and as per the connectivity at the ends of the member, the program can calculate the effective length factors. So here in design, we have the definition of frame, and we can specify if we want the program to auto calculate the effective length factors. So the auto calculation of effective length factors, it saves your time and you need not manually calculate the effective length factors and then provide to program. So this saves time. And then we have member assignment. Let's say we have one member, and in order to model the secondary beams, we have to divide this one member into 3 elements. So the program can auto detect that what 3 elements should be considered as one member. So the program will identify that these 3 elements should be designed as one member, and we need not do this manually. So the program can auto define the members, and this also saves a lot of time and the chances of human error are not there. And then we have the unbraced length. So if there is a difference of unbraced length for a member about 2x's, so the program can detect the different unbraced length. So let's say for column A, the unbraced length about y-axis, for bending about y-axis is L2, this one, and for bending about z-axis, the unbraced length is L1. So the program can detect this difference in unbraced length about 2x's and use that in design. So let's see member assignment in the program. So here in design we have member assignment. So we'll go for add replace automatic and the entire structure, and we click on apply. So we can see that the program has auto identified that what members should be designed as one. For example, here this member is modeled using 6 elements. So the program has automatically identified that all the 6 elements should be considered as one member. So this saves a lot of time. If we want to change the member definition manually, we can do that. And after that, we have the laterally unbraced length. So depending upon the bending moment diagram for every load combination, the program can calculate the laterally unbraced length. So the program will calculate A and the program will calculate B, and the laterally unbraced length will be calculated as A plus B depending upon the bending moment diagram for the member. Now these are the applicable limit states. So the program can check for rolled as well as built up sections, and these are the applicable limit states. So the first thing in the steel design is the classification of the member. The classification of the member depends upon both the material properties as well as the section properties. So considering both, the program can classify the sections as class 1, class 2, class 3 or class 4. So if the section is classified as class 4, then the program will calculate the effective section properties as per Eurocode 3 part 5. So in design, the program considers Eurocode 3 part 1, Eurocode 3 part 5 and BC1 2012. And now we have the first limit state, the axial force capacity of the section. Depending upon the class of the member, the program calculates the compression strength and the tension strength. And then the program compares the compression strength or the axial strength with the requirement, with the most critical case. And then the program also checks for the buckling resistance of members in compression. So first of all, the program calculates the slenderness of the member For calculation of the slenderness, the program requires the elastic critical force. The elastic critical force is calculated, and then depending upon the class of the program calculates the slenderness of the member. If the slenderness of the member comes out to be greater than the allowable slenderness, then the program calculates the design buckling resistance depending upon the class of the section, and here the program adopts the buckling curve as per Eurocode 3. And now we have the shear capacity of the section. After axial capacity, we check the shear capacity of the section. The program calculates the shear resistance of the member and compares it with the requirement. And after the shear capacity, the program checks for the buckling resistance of member in shear. The program checks if the buckling check for shear is required or not. If the buckling check for shear is required, then the program performs the buckling check for shear as per Eurocode 3 part 5. And after axial and shear, we have the bending. So the program checks the bending capacity of the section depending upon the class of the section. And then we have the lateral torsional buckling. So here the program calculates the slenderness of the member. If the slenderness comes out to be greater than the allowable slenderness, then the program calculates the design buckling resistance. Now, in order to calculate the slenderness for lateral torsion buckling, we need some parameters. So we need MCR. MCR is the elastic critical moment. And for the calculation of MCR, we need the parameters like C1 and LCR. LCR is the laterally unbraced length for lateral torsional buckling. I demonstrated the calculation of lateral torsional buckling unbraced length earlier. And then we have C1. The factor C1 depends upon the bending moment distribution in the section. So depending upon the bending moment distribution in the section, the program calculates the C1 and hence calculates MCR and finally the slenderness. So if slenderness comes out to be more than the allowable, the program calculates the design buckling resistance depending upon the class of the section. And then the program compares the elastic buckling resistance with the required force. After lateral torsional buckling, the program performs the checks for the interaction of the forces. The program performs the check for bending and axial interaction. After bending and axial interaction, the program checks for the bending and shear interaction. And finally, for the interaction of all three forces, bending, shear, and axial. And after that, the program displays the results in various kind of formats. So we can have the results in the tabular format or in the text report format or in the graphic report format. Let's see steel design in the program. So let's perform the design for our structure. In design, we have steel design parameter. So we can choose the steel design code as Eurocode 3 Singapore National Annex and the partial safety factor for materials. So the program already knows the partial safety factor as per Singapore National Annex. And we can specify the serviceability parameters. The default serviceability parameters as per Singapore National Annex are already there in the program. And then we can perform the steel code check. When we perform the steel code check, then the program will calculate the design ratios for the existing sections. So here we have the results. We can see that the results are color coded. So the results in blue are okay and the results in red are not good as mentioned here. So we can toggle the results between okay, not good and all. So here we can see that these sections are okay and these sections are not good. So we can even see the results in the graphical format if we want. We can display the pass or fail criteria here. So now, like for this section, the combined ratio is more than 1, then we need to change this member to some satisfactory section. So changing of the section is quite easy. We can just go for change, and while the program auto searches the section, you can restrict that the new section should be chosen from this database and this shape. If you want to put some constraint on the height, on the width, on the thickness of the new section, you can do that. And then after the specification, you can simply click on search satisfied section. So the program produces a list of the search of the satisfied sections. Then we can choose any of the section and we can simply change and close. So we can do this for all the members, but due to time, I'll just show it for one member. And then finally, when we want to update this section in our model, we can click on update, and then the program will perform the reanalysis and rechecking. One thing here to be noted is that every calculation is performed as per BC1. So we can save this table for report. I'll just save it as dynamic report table, and I'll show in the coming slides that how we can generate the report. So I'll just save it as dynamic report table for your reference. Now let's see how did we take care of the BC1 specifications. So here I select two sections and I generate the report for them. So here you can see that we have the member 344. So I'll save the report for this member. And then we have member number 363. I'll save the report for this member. Now I'll open the report for both of them. So here we have both the reports. This is for member 363 and this is for member 344. So here you can see that both the members are having the same material S275 as per BC1, S275 as per BC1, but they are having different yield strength. Member 344 is having a yield strength of 275 MPa and member 363 is having a yield strength of 265 MPa. So 265 MPa and 275 MPa. Now the difference in yield strength is due to the fact that they have different thicknesses. This member is having a thickness of 20 mm and this member is having a web thickness of around 12 mm. So one thickness is less than 16 mm and the another thickness is more than 16 mm. Since BC1 recommends the thickness to change at 16 mm, so both the sections are having different yield strength. Now we'll see the detailed report for design. So here you can see that this is a very detailed report of the calculation. This is something which can help you to learn the steel design algorithm. So here you can see that first the program gives you a detailed report of the road combinations, and then we have the information of the project. Then we have the section properties, if it is a rolled or a built up section. Then we have the design parameters, and then the design forces, and then the program gives each and every classification very detailed. The program gives that from which part of the code that specification is taken and the classification is performed. So here you can see that for flange and web the classification is detailed step by step. So every step involved in calculation is listed, just like you perform the calculations in a notebook. So you list down each and every step. So this is the same. After classification we have the axial check resistance. So if the program uses this formula, then from which specification the formula is used. So it not only lists the value for you, it lists the entire calculations for you. It helps you in learning the design as well. Then the shear resistance, and then the bending moment check about major axis, about minor axis, then LTB resistance, lateral torsional buckling if it is required or not, then the combined resistance, and finally the deflection check. So you can save the report if you want. So now after steel design, let's see what we have. So after steel design, we have the steel optimal design. So the program can perform steel optimal design as per strength optimal and as per displacement optimal both. So as a result of the design, the program gives us detailed reports. So here you can see that the program gives us the optimal design result as the weight sum. The program will give you the initial weight and the final weight, so that you can compare that how much optimization has been achieved. Now let's see optimal design in Midas Gen. So here we have the structure for which we'll be performing the optimal design. So we can go to design, and so first of all we need to perform the analysis, and then we can go to design and steel optimal design. So here we have the first checking results. So here one thing I would like to mention is that the optimal design can be performed for built up sections, and while performing the optimal design you can limit the database from which you want the new sections to be chosen. So you can limit the height of the section, you can limit the width of the section. So it is the user control is provided completely, and the optimal design can also be performed for built up sections. So we'll perform the optimal design, and you can specify the number of iterations, and you can provide the definition of built up sections if you want for the optimal design. Now I'll click on design and analysis. Here we have the results with us. I'll generate the graph report. So we have certain types of reports with us. So here the first is the weight ratio, the graph of the initial and the final weight ratio. So you can see that in the final structure, more and more members are located with the higher ratios, and less members are located on the lower ratio. Then we have the optimal design result, weight sum. So the program compares the weight of the initial structure and the weight of the final structure, so that you can see that how much optimization has been achieved. And this is the weight for every section. So you can see that the weight has been reduced, and this is the average ratio for each and every section type. So you can see that in time 1 the average ratios are higher, and these are the max ratio results, and even the maximum ratio results are much higher than the original structure. So this was regarding the optimal design. And finally we have the report generation. Let's see how the report generation feature of Midas Gen is useful. Let's say we want to generate the report for this project, and in the report we want to add this image. So we can just save this image as dynamic report image, and we also need some bending moment diagrams in the report. So let's say this one. So I'll save this image as dynamic report image, and along with that we also need some table in the report. So we have the table as well. So I'll save the table as dynamic report table. So here I can go to tools and dynamic report generator. I can open existing template or a new document. So when I'll open the dynamic report generator, Microsoft Word will open inside Midas Gen. So here you can open an existing template or a new Word document. So here we have the model description. So in the model description, we want to add a 3D image of the structure. So we have already saved the 3D image, so I can just drag and drop, and the image will be inserted in the report. And after that we have the section information, so you can drag drop the section summary into the report. So the section information with the diagram will be generated. Then we need the bending moment diagram. So you can just drag and drop the bending moment diagram. I'll do it again. So the bending moment diagram is inserted, and we also need some result table. We need the bending table. We need the forces table. So here you can see that the table has been inserted. Now how this saves your time is that, now let's say we make some changes in our model. So let's say we delete some part of the model, or any kind of change can be there. So let's say we deleted some part of the model, and now we'll go to report. So this is the original figure. So here you can see that the structure is not deleted, and we can auto update the report. So when I auto update the report, you can see that the figure is updated automatically. So not only the figure, but every other result will be updated. Every other beam diagram, table, everything will be updated automatically. So this saves a lot of time. So after the report, that was regarding the technical topics today. This is about the obligation of Eurocode from 1st April 2015. So if you need any kind of help regarding Eurocodes, so you can feel free to contact us. You can contact Mr. Edward Kim at the mentioned email ID, edward.kim@midasit.com, or you can just give a call to him. And regarding the ongoing training series, so we'll be coming up with more sessions. So we'll have a session on high-rise structures, and we'll also have the session on detailing requirements as per CPAT 3. We will see that what things do we need to take care when we generate the drawings as per CPAT 3, and how we can do it in Midas Gen. So this was regarding the technical presentation and the demonstration. Now we can have the Q&A session. If you have any questions, please feel free to write the questions in the questions window.